Functions in life are rarely simple. They often are the composite of one or more other functions, and we need to develop rules to deal with that. We're going to develop a rule called the chain rule that does exactly that. So let's talk about the chain rule and functions that are made up of functions called composite functions. And to learn about the chain rule, it's helpful to look at a situation involving gears and think of the gears as parts of the composite function. When gear A, this big gear on the right, makes X turns, gear B makes U turns, and gear C makes Y turns. That third gear C, the one on the far left, turns half as fast as U. So dy du, the rate of change of Y with respect to U, is 1 over 2. The gear in the middle turns 3 times as fast as X. So du dx, the relationship between U and X, is equal to 3 over 1, or 3, because B is going to make 3 turns in the amount of time it takes A to make 1. So if we wanted to find the relationship between the left-hand gear and the right-hand gear, C and A, we'd try to find dy dx, the rate of change of Y with respect to X. And it's a function of all 3 of them. So the rate of change of Y with respect to X is equal to dy du, the first 2 gears, or C and B gears, rate of change, times du dx, the B and A gears relationship. If we multiply them, we get 1/2 times 3, or 3 over 2. So gear C turns 3 halves, or 1.5 times as fast as gear A. And we did that by multiplying the rates. Let's put it in words. The chain rule. If we're given that Y is a composite function of U, a differentiable function of U, and U is a differentiable function of X, so then Y is a composite function of U of X. If that is true, then dy dx, the rate of change of Y with respect to X, is equal to dy du, the rate of change of Y with respect to U, times du dx, the rate of change of U with respect to X. Let's look at an example. Let's say we're given this function, the quantity 6x to the third minus 4x plus 7, all cubed. Now you could distribute that out, be a little bit difficult. You get a bunch of terms, and you could individually, using the sum rule and the power rules, find the derivative, but a faster way is to use the chain rule once you've learned it. We're going to say U of X is going to be what's inside the parentheses, 6x to the third minus 4x plus 7. And f of U is going to be U to the third power. So we've simplified using the chain rule, making this a composite function. We simplified this into f of U equals U to the third, because we know how to take the derivative of that. The derivative of U to the third is 3U squared. And so we have 3 times U squared times the derivative of U. So the 3U squared, this is dy du, the derivative of Y with respect to U. And then the second part is the part that a lot of people forget, to go ahead and take the derivative of the inside part, the U. The derivative of U, since U is 6x to the third minus 4x plus 7, is going to be 18x squared minus 4. And so this is the derivative of this original composite. Let's do another example. And let's say we have the composite function f of g of x equals the sine of x squared minus 4. Now we cannot find the derivative of that without the chain rule. So we're going to let y equals sine of x squared minus 4. And we're going to let u equals x squared minus 4. So y becomes the sine of u. So the inner part, the part in the parentheses, is x squared minus 4. And we've simplified that down, letting u equals x squared minus 4. Y then becomes the sine of u. Well, we know that derivative of the sine is the cosine, so dy du is cosine u. And we know du dx is the derivative of the u part is 2x. So using the chain rule, the derivative of this composite function is dy du times du dx. We're going to multiply the rates. So it's cosine u times 2x. but we've got to go ahead and substitute back for that u. So the derivative of y with respect to x is equal to the cosine of x squared minus 4, which is u, times 2x. Now we've taken the derivative, but that 2x does not belong inside the input of the cosine. It belongs on the outside. So let's rewrite it as 2x times the cosine of the quantity x squared minus 4. Let's look at another example, the derivative of cosine squared of 3x. Now we'll rewrite that as the derivative of cosine of 3x all squared. That's going to help us view this as a composite function. Now, in fact, this is a composite of a composite. So it's a little bit more complicated because not only do we have the whole thing squared, it's the cosine of something more than just x. Using the chain rule and the power rule, it's going to be 2 times the cosine of 3x times the derivative of cosine 3x. So it's the derivative of the outside function times the derivative of the inside function, but we're not done yet. We've got to deal with this derivative of the inside function part. So we use the chain rule again. The chain rule can be used many, many times. So now we're going to take the derivative of this part. So it is equal to the derivative of cosine of u, which would be the negative sine of u, times the derivative of the inside part of that, which is 3x. The derivative of 3x is 3. So in the end, when we combine these terms, we're going to get negative 2 times the cosine of 3x. We move the negative sign out front. Times the sine of 3x times 3. And we can simplify that further as negative 6 cosine 3x times sine of 3x. It's a common mistake to forget to use the chain rule in problem. In fact, you can look at every derivative problem as a chain rule. For example, the derivative of x squared dx could be looked at as the derivative of the outer part, 2x, times the derivative of the inner part, x. So it's 2x times the derivative of x with respect to x. But the derivative of x with respect to x is 1, so it becomes a simplified problem. So don't forget to use the chain rule when you need it. So now you know how to use the chain rule to find the derivative of much more complex functions than you could before.